Welcome back, everybody. We're continuing with Chapter 5, Maps and Geographic Techniques. We're up to Part 5 now. The next topic is the subject of map scale. All true maps are scaled down drawings. They have to be scaled in some way. You're probably familiar with this somewhat already. If you've seen any map somewhere down in the corner, it lists what the scale is. So you can visualize, say on this graphic scale, how far it is from one place to another, and also think about what aerial dimensions might be as well. The map scale tells you the relationship between distances measured on the map and distances out in the real world. Something else that map scale does for you is it tells you how generalized the map is. Okay, when you may have some familiarity with this when you're dealing with your cell phone maps, say your navigational maps, when you know that when you zoom in to a locale, then you get more features labeled, more streets are on there. But then when you zoom out to cover a larger area, a lot of those labels, a lot of that detail disappears. So when you're dealing with maps of the world, on any theme, they're very highly generalized in that they have to leave out a lot of detail. However, when you zoom in to maps, you can include much more detail. Well, the map scale is indicative of how much generalization there had to be. Now, there are three ways to express scale. There's the verbal scale, graphic scale, and the RF. The graphic scale is probably the one that you're most familiar with, and somewhere down in the corner of the map they'll have a line segment, and then units are ticked off in miles or kilometers or whatever the units are. The great thing about the graphic scale is that it enlarges and reduces right along with the map. Say you had a map and you wanted to cut it and paste it into some type of paper or report or presentation. Well, when you cut and paste the map, you cut and paste the graphic scale right along with it. That's not so with the ratio scale, although a lot of people are familiar with the ratio scale representative fraction if they like to build scale models or model railroads and so forth. Well, here the map scale is given as a fraction or as a ratio, in this case 1 over 62,500. That means that 1 inch on the map is equal to 62,500 inches in the real world. What about centimeters? Well, then 1 centimeter on the map is equal to 62,500 centimeters in the real world, or whatever units you're using, paperclip lengths or pencil lengths. Well, 1 paperclip length on the map is equal to 62,500 paperclip laid end to end. That's the ratio scale. The thing about this is that, and a lot of people don't realize this when they're cutting and pasting maps, and I see this all the time, where it has a ratio scale down in the corner of the map, and that of course is not right. It was correct when the map was originally drawn, but if it's been enlarged or reduced, all of that has to be recalculated. So usually with the graphic scale, if that's what you have, in most cases that's what there is there, it enlarges and reduces right along with the rest of the map. The verbal scale, sometimes it's just a verbalization of the RF, where somewhere down in the corner of the map it may say something like 1 inch equals 1 mile, or 1 centimeter is equal to 5 kilometers. It's a verbalization of the RF. Well, sometimes we need to talk about scale relationships and large scale things and small scale things, and this is part of our everyday experience, how we talk about scale. For example, let's say that you were a student, you were doing a research problem on hunger issues. Why is it that people go hungry? And you did an analysis of our local area and you came up with some conclusions, and then you published that information. but your advisor told you, well, you did a very good study here. Why don't you think about doing this on a larger scale? What would you think that meant, a larger scale? Wouldn't you think that means bigger? Well, how about national or global? Because the generalizations that you can make about hunger, the generalizations you can make at the global scale are probably different generalizations and different reasons why there's hunger on the local scale. So, the scale of the generalization is going to be important. Well, here's the odd thing about that. When you go from, say, a local scale, say Robeson County scale mapped, to a world map, you're actually going to a smaller scale. Now, we don't usually talk like that in our popular speaking. Usually when we say larger scale or go to a larger scale, that usually means big things. But in cartography, it's the opposite. And let me show you why. This is the example that they have in the textbook, but I don't like this one. I'm just going to go to the slide here. I think this one is probably better. This is from a different source. All right, so which one's the large scale map and which one is the smaller scale map? Well, we can get rid of these two intermediate ones because we know that that's not on one end or the other. But here we have a map of the continent, and then here we have a detailed map of Montreal. Now the maps are of the same size on the page. Which one is the larger scale? Now you would probably think that, well, the map of the continent, that's the larger scale, right? Because it's larger things. No, not in cartography. A map of the continent, maps of the world are small scale maps. They're highly generalized and a lot of the detail is missing. Whereas larger scale maps show a lot more detail. They show smaller areas, but a greater amount of detail. All right, so larger scale maps show a lot more detail. In this case of this Montreal map, all the road network and so forth, there's a lot of detail. You can't show that on the map of the continent. Now, where do they get the idea of calling it large scale and small scale, especially since we don't talk like that? Well, you have to look at the RF. Now let's look at the RF of this map when it was drawn. It was 1 over 1 million. Now 1 over 1 million, that's a tiny number, but it's a lot larger than 1 over 103 million. All right, so we'll say this one is the smaller scale. This one is the larger scale. All right, but yes, I know that in our everyday speaking, we don't talk about scale relationships as they do in cartography, large scale maps and small scale maps. And a lot of times when we think about large scale industry, we mean big ones. All right, but sometimes I may use the phrase large scale mapping. When I say large scale mapping, that means zoomed in with a lot of detail. Okay, all right, let's move on. These are some practice mapping questions about what's large scale and what's small scale. You can take a look at that. Now, to completely change topics at this point, the next topic is topographic maps. These maps that use contour lines to indicate the lay of the land, the surface features, and so forth. I don't do a lot with topographic maps in Geography 1010. If you're going into earth science or you're taking some of the geologies, you'll do a lot more with topographic maps. I've included the link for the United States Geological Survey website there. All right, but I want you to understand the basic concept behind what a contour line is and how it shows topography. Here's another example for a part of a 1 to 24,000 scale map. almost all of the United States. I think the only part of the United States that's not mapped out at 1 to 24,000 is in Alaska, where there's not a lot to map, I suppose. But these are fairly detailed maps when you spread them out onto a desk and you can look at the features. Usually in class I'll pass around the Pembroke quad at 1 to 24,000. You can get an idea of what surface features are like. And there should also be a scale, a legend. Yeah, it does have a scale on the topographic map, but there's a legend that tells you what the various symbols on the map represent. Okay, well, let's talk about the underlying concept of what topographic maps are, what contour lines are. This is a graphic from your book. All right, these are contours drawn for a place. Are you looking at two peaks or two pits in this case? And how would you be able to tell? Well, you're saying, well, those are two peaks because here on Twin Peaks Island, you're looking at the contour lines, and you're at sea level here at 0, and you go up 100 feet, so the contour interval must be 100 here, and then you go up to 200, and you go up to 300, then you go up to 400, then you're running out of hundreds after that. So these areas can be mapped out. So okay, well, I can see, I'd be going up here, I'd be going downhill this way. Right, and so that's what contour lines do for you. You have the reference point or the reference datum. In this case, it's average sea level, and then as you go on up, you have a contour line that's drawn every 100 feet. All right, that's pretty easy to see. Oh, for those of you that are in K-12 education, and if the subject of topographic maps comes up sometime, and you need to explain to kids topographic maps, let me share with you a story that my old geomorphology teacher told me many, many years ago. It's the story of how contour lines got on topographic maps. And he told the tale of the mad painter and the mad photographer. All right, let's talk about what that is. And then someday maybe you can tell the story of the mad painter and the mad photographer and how contour lines got on topographic maps. All right, there's this guy, he's the mad painter, and he's obsessive compulsive. And that whenever he goes to a new area, he's obsessed with spray painting a brown spray paint line on everything that's at the same height on the land surface. So he goes here to this island, he decides on his contour interval, looks like it's 25 in this case, and he goes around and he spray paints everything that's at 25 feet elevation till he gets all the way around to the other side of the island. And then he goes up to the next island. He spray paints everything on the ground that's at 50-foot elevation. Now, you as a teacher, you can embellish the story depending on the grade level that the kids in your class are. But you can tell a little story. Well, whatever's there, it doesn't matter if it's a parking lot, if there's a little dog in the way, he gets sprayed too. He'd yo. It doesn't matter if it's a policeman's feet and it's on the ground. Well, it's 50 feet. He gets sprayed, and then they would say, you can't do that. Well, anyways, you can embellish that story. All right, then he goes up to the next one, and the next one, and the next one. And so he's spray painted these brown lines on everything on the ground that's at that elevation. Now, he has a friend that's the mad photographer. The mad photographer has a special camera that when it takes an aerial photo, it only picks up the magic paint of the mad painter. And so it only shows this, doesn't show anything else. So all it does is produces an image of the lines. And so what you have there is a topographic map of the contour lines. Okay, now someday, if you're teaching topographic maps, you can tell the story of how contour lines got on topographic maps and the mad painter and the mad photographer. Only you'll be able to tell that story well. All right, just a little bit of a test for you here. What is the contour interval on this map? Well, first up, you have to look up the definition of the contour interval. Okay, that's the vertical interval between the contour lines. All right, it tells you how much vertical change there is over horizontal distance. So in this case, you have one contour line 700, this one 800. So eyeballing this, looks like the contour interval is 20 units. In this case, if it's feet or meters, let's just say it's feet. So you go from 700, 720, 740, 760, 780, and then 800. Now, what does it mean when the contour lines are close together or spread apart? When the contour lines are close together, that means that you have a steep drop-off. And then when the contour lines are spread far apart, that means you have a more gradual slope. So the spacing of the contour lines tells you about the gradient. Okay, you could push a boulder down the hill a lot faster. If it's steep, it'll roll down a lot faster than if the gradient isn't so steep. You might have to give it more of a push. Another way that topography and elevation is shown on maps is what's called a shaded relief map. Now, they took the picture of the shaded relief map out of your current version of the textbook, but I'll put it back in. It's pretty easy to see what they do. Is that they take a map, a topographic map with the contour lines, and then they add in shading patterns of what it would look like if these features were to cast a shadow, if these mountains would cast a shadow. So that means that, well, those mountainous features, they really jump out at you that way. So elevation on topographic maps, they may be shown by contour lines, these brown lines here. We know what the elevation is along those points. Also benchmarks and spot heights. What's a spot height? You have a couple places here that are mapped out as a spot height. For example, here you just have a point. It's a spot height. That means right at that place, right at that point, it's 1,604 feet. Which it used to be, I used to get confused by the spot heights because I thought, is this State Route 1604? Yeah, no, that's a spot height. Now, there are some places where the spot height is given with an official marker from the U.S. Geological Survey. A bronze marker is put in the ground, and the USGS keeps track of these benchmarks. All right, as part of their geodetic control data of understanding what the configuration of the Earth's surface is. And here's a picture of a benchmark. Another way to visualize topography is with what's called an orthophoto map. Ortho means rectified or corrected. That's when you take regular old topographic map information and contour lines and you add in color air photography. When you do that, it makes the features stand out a lot better. In this case, especially low-lying areas where you don't have very much elevation change over from the land, over to the river, then out to the ocean. There's only a few feet difference. So in order to show that, it's hard to visualize it with topographic lines, but if you put in the color air photography, it makes it a lot easier to visualize. Okay, so that's one of the terms in the chapter. It's orthophoto maps.